In this video, we're going to go over some more binary search tree methods, starting with removing an element. Now, removing an element is probably the most complicated of all the methods in our binary search tree class. So we're going to go over this pretty slowly. And first off, we want to talk about what this method needs to do. So if we have an empty tree, we're going to throw an exception. That's the easiest case. And if we want to remove the root, keep in mind that the root is really the only node that the binary search tree has a reference to. It accesses all the other nodes through the root. So we need to find the in-order successor. That would be the node that holds the element that would come after the root if we did an in-order traversal. And then we're going to replace the root with that in-order successor. Now, this example was pretty simple. We'll do some more complicated ones later. Now, if what we want to delete is not the root, say for example, we want to delete 2 here, then first we need to search for that element. And so 2 is less than 5, so we go in the left subtree and there we find 2. Then we replace 2 with its in-order successor. Now, what if the in-order successor has children? So in this tree, we want to delete 5. 7 is the in-order successor, but you can see that it has a right child. Now, the in-order successor would never have a left child, because if it did, that left child would be the in-order successor. So what we're going to do is we're going to rearrange these 3 nodes. So the left child of the node we're deleting, the left child of the parent of the in-order successor, and the right child of the in-order successor. So what we're going to do is we're going to rearrange this so that the left subtree of the node we're deleting becomes the left subtree of the in-order successor, and the in-order successor's right subtree becomes the left subtree of the in-order successor's parent. So we move 8 into the left subtree of 9, and again, there's only going to be a possible right child. There will never be a left child. So that's just a simple replace. And then we make the node we're deleting's left subtree be the left subtree of the in-order successor, which here is 7. And then we do our replacement. So let's take a look at the removeElement method. So if we have an empty tree, we're going to throw an exception. And then otherwise, we're going to check to see, does the root contain what we're looking for? If so, we're going to find a replacement, and we're going to make that replacement the root. Otherwise, we're going to make a recursive call to a overloaded removeElement method. This time it takes the target element, the subtree that we want to search, and the parent node, which would in this case be the root. And so this overloaded method is going to look a lot like what we've seen before. We're going to check to see, is the target at the root of that subtree, which we call node here. And if it is, then we find the in-order successor and replace the node we're deleting with the in-order successor. Otherwise, we continue to search. And again, we'll continue to compare the element to see if we need to search in the left or right subtree. And we'll continue to do that until we either find the element and remove it, or if we run into a case where the node is null, that means the tree is empty. That means there's nothing to delete. And so we'll throw an exception that the element wasn't found. So let's go into a little more detail with how this works, including this replacement method. So if I want to delete the root element, I'll find the in-order successor, and then I'll replace the root with that in-order successor. Now, replacement doesn't just find that node, it also will set its left and right children so that we can do a drop-in replacement with that in-order successor. So it's going to find a replacement for the root, which is the in-order successor, and then it'll replace the root with that in-order successor. If the root element is not what we're deleting, then we're going to look in a subtree. So in this case, what we want to delete is in the left subtree. So we're going to want to remove an element from the left subtree of the root. So now we're in the overloaded method. So the parent is the original root. The node we can think of as being the root of the subtree we're searching in. And that's exactly what we're looking for. So we're not going to be doing any more searching. We're actually now ready to call replacement. So let's talk about this replacement method before we go any further. So replacement is going to give us a node that has the children set to whatever it's going to be, and then it returns a reference to that in-order successor. There's 3 cases that we're going to look at. First off, if there's no children, there's no replacement node, so we're going to return null. If the node we're removing has only 1 child, and that child is the left child, then we're going to return the left child, and we'll do the same thing with the right. The complicated case is if we have 2 children, and then what we're going to do there is we're going to get into the right subtree of the node we're deleting and go all the way to the left. So we'll walk through this code to show you how to do this after we look at some examples of these first three cases. In the case where there's no children, we're going to return null because there's nothing to replace this with. If we're deleting a node with one child, then we're going to replace it with that child. So if it's on the left, it'll be the left child. So if there's one child and it's a right child, such as in this case, we'll return that right child. So the complicated case is something like what we had above, where we're deleting 5. So in this case, the in-order successor is 6. So how do we get to 6? So replacement, again, starts with a root, and again, not the root of the whole entire binary search tree. We're talking about the root of the subtree where we're searching. So we set a reference to current, and we set that to the right subtree of the root. And remember, this is because we want to go to the leftmost node in the right subtree of the node we're deleting. The parent is going to be set to the root, and then we're going to, in a loop, go as far to the left as we can, updating the parent and the current as we go. Since current does have a left subtree, we're going to set parent equal to current and current equal to its left subtree. Current still has a left subtree, so we're going to do it again. And now we're at the case where current doesn't have a subtree, so we're going to exit the loop. So now we're going to set current's left to the original root's left subtree. So that's this subtree right here. We're going to move that so that now it's the left subtree of the current node. Then, if the original root's right is not equal to current, which in this case it's not because this is the original root's right, then we're going to set parent's left equal to current's right. And in this case, there's nothing there, so there's nothing to do. And then we're going to set current's right to the original root's right. So now we're ready to replace the node we're deleting. Now, one thing I want to say, the reason we're doing this particular check, if there was a case where, for example, let's say 18, if we were deleting 18, this loop would never actually execute because there's no left child. And so at this check right here, the root's right would be equal to the current, and so we would just leave things alone. You may see some places where you're wondering, well, why isn't it handling this child or that child? Most of that confusion is just because it's really easy to forget you're working with a binary search tree with in-order successors and so forth. So there's a lot of these cases where we know that there's not one subtree or the other because we're dealing with a case where there's only one subtree, or if it's an in-order successor, we know there can't be a left subtree. So if you run into a case where you're wondering, hey, why are we just ignoring this particular possibility? Double check what you're actually looking for. Keep in mind that it's a binary search tree. We're dealing with an in-order successor, and you may realize, okay, there's not really a reason for that node to have a child there. Okay, so back to our original. So at this point, we're going to set the result equal to the current node, and that's what we're going to return from removeElement. So now we're back in removeElement. Remember, we have this parent and this node that we're deleting. And so if the parent's right is equal to the node, which is not the case here, we'll go to the else case. So parent left is equal to the in-order successor. So what we're going to do is we're going to change this link to where now the left child of 10 is going to be 6, not 5. So 5 is now junk, and you can see now we've replaced the left child of 10 with 6. And now we have removed 5 from that binary search tree. This is definitely a method that you will want to do some examples of, trace through it. Just looking at the code and trying to trace through it in your head is going to be impossible in a lot of cases. And so definitely make sure you're reviewing this and walking through some examples just like we did here. So we also have a removeAllOccurrences method. And what that does is we remove one element, but removeAllOccurrences is going to remove every occurrence of that element in the tree. So after it moves the first one, and again, remember, if there's not one, it'll throw an exception. So then we're going to have a try block, and we're going to run a infinite loop where we try to remove the target element. Now, eventually we remove them all, so this will throw an exception. So that exception will get caught, and you'll notice we don't do anything with the exception in this case. If this remove throws an exception, we do propagate it because that means that element doesn't exist in the tree at all. But then here we use that exception handling to exit out of this infinite loop once we've deleted all the existing elements. Now, removeMin is an interesting one because it looks complicated, but it's actually a little simpler than it appears at first. So let's take a look at these two binary search trees. The minimum element in this binary search tree on the left is 1, and we can find 1 by going all the way to the left. And of course, if we were going to remove that, it's a straightforward remove because there's no children. Now in this case, our min element is A. So when we remove A, we'll need to replace A with B. But again, that's going to be straightforward because A only has one child. And remember, removing when there's 0 or 1 children is straightforward. And the node that has the minimum element can never have more than 1 child. Because if it had 2 children, then that left child would be the minimum. And so the minimum can't have 2 children. Now, the other case we have to consider is, what if the root is the minimum element? So that's handled in this case here. If the root doesn't have a left, that means the root is the min element. And so we return that element and then set the root to its right. Otherwise, in this loop, we look for the minimum element, and notice what we're going is as far to the left as we can. Once we do that, we grab the min element off the leftmost node, and then we set the parent's left to current's right. Now, if current doesn't have any children, that's null, or it might be a subtree, in which case this handles both cases correctly. And again, anytime we remove, we're doing a modification, so we increment our mod count. So removeMax will be one that you'll be asked to implement on your own, as well as findMin. So findMin, findMax, they work very similar to removeMin and removeMax. They just don't actually remove anything. They just return that element. Find, you'll be asked to do as a programming project. The key here, don't call the binary tree version of find the superclass find, because that doesn't make use of the properties of a binary search tree. So your find should not search through the left, and if it doesn't find it there, search through the right subtree. You should only search in the left or right subtree based on the result of a comparison with the root element. And so you also have get left and get right procedures that return linked binary search trees. And the reason we're overloading these is because in binary search tree, they are returning a binary search tree. We need this to return linked binary search trees. So that completes the code for the implementation of a linked binary search tree. Again, some of this code is very complicated, and so I definitely recommend that you try to trace out some of these examples on your own. I would recommend that you take a few elements, add them one by one, trace what happens, and then trace what happens as you remove them one by one.